Hello again, this is Mr. Lowry. Hope you guys are doing well out there in quarantine land. We only got a couple more weeks, well maybe like a week and a half now, so if you're going crazy, hang in there. We're almost there. I'm going to do a bunch of stuff for you at the end of the semester. I'm going to drop a bunch of homeworks, I'm going to drop a little quiz, I'm going to drop a little test, so I think you'll do okay if you hang in there. Today we're doing some exercises and some proofs, taking some ideas from 12.3 and 12.4 in your book. I've put some page numbers here for you to reference if you want to go and check that out. One of the main ideas that we're going to talk about today is this side angle side congruence theorem. We're going to go through this in just a second and we're going to talk about it kind of in detail. But in order to build up to that, we want to review or talk about some ideas that we already know, because remember, in an axiomatic system, you got to build on what you already know. Okay, so let's go back to the last page of the previous assignment, okay, which is this guy, and there's some important information that we need to know. Okay, the first thing is congruent figures. Okay, now we're specifically going to be dealing with triangles a lot in this section, and so I'm going to change this to congruent triangles. Okay, a figure can be, like a circle, or it can be a quadrilateral or a different shape. We're going to kind of keep our discussion to triangles here. So we're going to say two geometric figures. So we're going to say triangles are congruent triangles if and only if there is a rigid motion or composition of rigid motions that maps one figure onto the other. So if we take a triangle, great triangle, and we reflect it, we're going to get a congruent triangle, right? If we rotate it or translate it or some combination of those, we're going to get congruent triangles. Okay, that's an important idea. This is another important idea. Corresponding parts of congruent figures are congruent. Now again, we can change this to triangles. Okay, corresponding parts of congruent triangles are congruent. So if you're like, well, hey, this angle corresponds to this angle, then these two angles have to be congruent. And if this segment corresponds to this segment, then these sides have to be congruent. That kind of thing. There's actually an abbreviation for this, corresponding parts of congruent triangles congruent. It's CPCTC. And you might see this from time to time. What this means is corresponding parts of congruent triangles are congruent. So once you know two triangles are congruent, you can say that the corresponding parts are congruent. Okay, that's important. Another thing we need to look at is this kind of thing. So right now, the only way we can say that two triangles are congruent, the only way we can prove that two triangles are congruent is one of two things. Either we prove that there's a rigid motion that maps one to the other, or we have to show that every piece has a corresponding congruent piece. Show all sides and angles have a corresponding congruent side and angle. Right? So if I'm looking at these two figures, the only way I could say that these two figures are congruent is to be able to say I have to have all the tick marks, right? I have to have all the sides congruent and all the angles congruent. That's 6 pieces that I have to have congruent. Okay? Now in this case, if we look at kind of the different vertices, we can kind of see how the vertices line up. So in this, we have this triangle here, we have B, C, and R, and notice that the C has 2 marks on it and the S has 2 marks, so we know that C corresponds to S. Okay, the B has 3 markings on it and the T has 3 markings, so then B corresponds to T, or like T is the image of B if we're thinking about this as a transformation. And then we know that R corresponds to R. Okay, so if we wanted to write a congruent statement, what we would say is that triangle, you could say like CBR is congruent to triangle STR. And remember that the order is really important here in terms of like the C and the S have to be in the same position, and the B and the T have to be in the same position, and the R have to be in the same position. So I could write another congruent statement that's a little bit different, like I could have RBC, and that's fine, as long as the, sorry, I need a triangle symbol, as long as the letters on the other one are in the same position as their corresponding angle. So this would have to be RTS. Okay, so either of those is true. Okay, so here's the first big question that we need to think about. Okay, the first big question is this: is there a minimum amount of information that we need to show that two triangles are congruent? In other words, is there a shortcut? Do I have to have every single side and every single angle before I show that two triangles are congruent? Or can I say, okay, if I only have a little bit of information, I can still say these triangles are congruent? Okay, that's the question we're going to answer. Can we have less information and still know that two triangles are congruent? Okay. All right, to answer that question, I'm going to give you another question, okay? I'm going to give you something to think about here. So what I'm going to do is I'm going to create a fixed angle with two fixed segments, okay? So there's nothing special about these. I'm just going to make them up, okay? So what I have right now, make sure that I don't get the glare on that. What I have right now is I have a fixed angle and two fixed lengths. This length is not the same as this length, but it doesn't matter. And then there's an angle here, okay? The question I have for you is, how many ways, let's put a point here, how many ways can we complete this triangle? Well, the answer should be only one. There's only one way we can complete this triangle. I already have the three vertices. If I have a set length here and a set length here and a set angle, the only thing I can do to make a triangle is just to connect these two dots, okay? So if I have a side that's set and a side that's set and an angle that's set, there's only one other way to complete that triangle, okay? Let me kind of explain that one more way, okay? Let's say I wanted to copy this guy, okay? Or let's say I wanted to copy this guy, this angle, and this side, okay? Now we could do that by construction with our compass. I'm not going to do that with a compass because it's going to take too long and it's not super important that it's perfect right now. But let's just kind of see. So about this length here, okay? And let's just say kind of theoretically we are copying this. Again, this is not a perfect construction, but we could make it a perfect construction if we were. Okay, so let's say that I knew that this guy was congruent to this guy because I copied it, and this guy was congruent to this guy because I copied it. Let me get that out of the light for you. And then this angle was congruent to this angle. Okay, the question is, again, how many ways are there to close up this triangle? Well, there's still only one way to close up the triangle, right? The only way you can close up this triangle is to connect the dots, okay? So if I know, let's call this triangle ABC, and let's call this triangle DEF. If I know that this side is congruent to this side, and this angle is congruent to this angle, and this side is congruent to this side, I know that these two triangles are congruent to each other. Because this one kind of has to be congruent to this one. There's only one way to draw that segment. They have to be the same length. And that kind of makes this angle have to be equal to this angle, and this angle have to be this angle, because there's only one way to finish that triangle. Okay? And that's not like a super rigorous proof, but that's kind of some reasoning behind what we're going to talk about today, which is called the side-angle-side postulate, or the side-angle-side theorem. Okay? So you got side, and then an included angle, and then a side, okay? If we know that two triangles have a side and an included angle and another side congruent to the side and included angle and side of another triangle, we can say these two guys are congruent. Okay? That's kind of the side-angle-side theorem, right? Let's talk about that theorem in a little bit in detail, and I'm going to pull out your book for this. Okay, so this is on page 602. You can reference this if you want to. And this is the side-angle-side congruence theorem. Okay, so they say if two sides and the included angle of one triangle are congruent to two sides and the included angle of a second triangle, then the two triangles are congruent. This gives us kind of like a minimum amount of information to say that two triangles are congruent. A super important part of this is this keyword included. Okay, what does included angle mean? All right, included angle means the angle has to be in between the two sides. Okay, it can't just be any random two sides and an angle. It doesn't work like that. The way we constructed this, we made sure the angle was in the middle. If you move the angle around to different spots, there are more than one way to complete the triangle. But if you have side, angle, side, in other words, the angle is in between the two sides, or the angle is the angle created by those two congruent sides, then you know the two triangles are congruent. So it has to be the included angle, or the angle that is formed by the two congruent sides that you're talking about. Okay, now there's a proof here of this, and it's really hard to follow. In a lot of books, and depending on which book you're working with, sometimes they'll call this the side angle side postulate. They'll just show the reasoning that I showed you and say, look, it's pretty obvious to everybody that there's only one way to finish this triangle. So this is a pretty common notion. I don't really have to prove it. I can show you that if two triangles have side angle side, right, or two sides in an included angle, that they have to be congruent. This kind of uses a similar idea, but it uses more transformations as well. Let's see if I can walk through this here. Sorry. Okay. So what they do is they say, okay, here's your two triangles, right? And they do a bunch of congruence transformations. So they do a translation to put them together. They do a rotation to flip one of them around, and they get this figure. And then they're saying, look, hey, I'm doing rigid motion, so I'm not changing the triangle at all. All my segment measurements, all my angle measurements are preserved. When they get down to this point here, basically what they're saying is, since every point on the segment DF is on the line of reflection, then they are their own image. So D is the image of D and F is the image of F. Okay? Then they say, hey, look, since you have this segment measurement and this angle measurement fixed, because they're marked, congruent, that means that E has to be the image, or sorry, B prime prime has to be the image of E. So basically what they say is they basically said the same thing that I did, kind of. They say, look, D maps to itself, F maps to itself. We can show you, because this length and angle are set, that E has to map to B prime prime. And so you get these 3 points where they're like, look, these 3 points give you these 3 points by this reflection. And there's only one way to complete a triangle when the 3 vertices are like in a fixed position. Okay? So once you have the 3 vertices as like kind of like what we did in our homework, if we have those 3 vertices, you just connect the dots and you get your triangle. So they used rigid motions and transformations to show that this other triangle that we had floating around here is just the image of these 3 points. And if we connect the 3 points, then we get a congruent triangle. Okay, so it's a little bit more involved, but it kind of uses pretty much the same reasoning. So we're not going to go through and prove that in detail. I'm not going to ask you to prove that. I think that this reasoning is a little overkill. We're just going to kind of take this as almost like a postulate and say, hey, we kind of understand what's happening here, because I showed you kind of that reasoning. All right, so that's the side angle side congruence theorem. Okay, and then in the next video, we're going to come back and we're actually going to use that theorem, and I'm going to help you do some of your homework problems. But I just wanted to introduce that for you and make sure that you understand what it's talking about and how we get there.